Okay, so there were a few things we need to finish off this lecture. We were doing the Mach-Zehnder interferometer. Now, uh, the way I have set it up, either the photon can come through this way, or the photon can come through this way. I'm just considering one photon at a time. So, one photon, either it comes from the upper port or it comes from over here. So, and this is my beam splitter. So what happens is essentially I can write down the state in forms of a vector, a column vector 1 0. Let me call it the this path the photon might take as A, and I'll call this as B. So these are two orthogonal paths in some sense the photon can take. So what does this vector mean? It means that I am injecting the photon through this port and there's nothing in this port, and the other combination would be nothing is coming from here from the port A, and a single photon is coming from port B, and that's going to be 1B. So these are essentially the photon in A, and I'll label it as photon in B. Now, I can ask the question, what exactly is the Mach-Zehnder interferometer? So, to get the rabbit out of the hat, the Mach-Zehnder interferometer for you guys is your first quantum computer. Of course, we need to make the interferometer work like a computer or put some other bells and whistles into it. But what essentially is a quantum computer? A quantum computer is where you have some input state, some operation, and some output. And when these states are quantum states, and the output is quantum, and over here is a quantum process, well, that's your quantum computer. Now, in this Mach-Zehnder setting, the way I have set it up, just imagine the time going this way. The photon is coming, it hits the mirror, and this is the way the time goes in this particular direction. Just a schematic how the time goes. So what's really happening? I have a beam splitter, and as you know from the postulates of quantum mechanics, the evolution of a quantum state is given by a unitary matrix. So I have a beam splitter, I'll just label it as a matrix. This is the unitary matrix representing the beam splitter. Let me just call it BS. So I'll have That's my input state. Photon here, one photon here, and maybe nothing here. And I'll have some sort of an output. I'll have T and I'll have S. Now, of course, unitarity demands that T square plus S square is 1. Essentially, that means is that the probability of having the photon in either of the ports is conserved. That's essentially what's happening. And I can do the same sort of an analysis for the other port. And that's going to give me U and V. Okay, so I'll have, that's what is demanded by unitarity. So this is how I represent the beam splitter, and this is how I represent the photon. Any particular state of the photon alpha, beta, essentially means I'm just removing the subscripts A and B. I won't be using it many times, but that essentially means that the probability amplitude, which is a complex number, probability amplitude of finding the photon in the A port or the A path in A is alpha, and probability amplitude in B is beta. So that's essentially the idea of the beam splitter. Yeah, you can have various examples of beam splitter. Essentially, any unitary matrix will serve as a beam splitter. Of course, whether it's a 50-50 beam splitter or not, that's going to be another condition on that unitary matrix. That's going to be one of your homework problems. But so, for example, this is a beam splitter. Question for you: is the matrix is a beam splitter? So essentially the idea is that I took a optics problem, a quantum optics problem, and I am arguing that this is our first elementary quantum computer, and I am replacing the circuit elements, the beam splitters, the mirrors. I can replace them by valid quantum operations. Like the beam splitter was a unitary matrix out here. The mirror would also serve as some unitary acting on a quantum state. And let's say, for example, if I have a phase shifter, like I introduce some glass plate in the path of the photon, this phase shifter that's just going to put some sort of a phase relative to port B on this path over here. So we'll see these things in detail, but essentially that's what's happening. Here was the direction of time, and as my quantum state from here propagates through a unitary operator, again a phase shifter, another unitary operation over here, and this beam splitter is, let me call it U1, this is U2, another unitary operation U3, I can conveniently represent it as a circuit. And the circuit would be the first beam splitter, then a phase shifter, then another beam splitter, so on and so forth. So this is my input state, this is my quantum process, and this is my output. I forgot to include the mirrors, but you can put the mirrors over here. That they're going to be another operation. So this is going to be mirror M1, mirror M2, some other unitary processes. So that essentially is called a quantum circuit diagram. We'll be seeing these in more detail, but quantum circuit diagram, sort of a flow chart where the time is flowing in this direction, telling you what exactly is happening in a Mach center interferometer or a Mach center quantum computer.